Welcome all of you for today's live session. This is the fourth live session for this Smart Grid Basic to Advanced Technologies course. And I'm the one of the TAs for this course. My name is Gagan Meena and I'm a fourth year PhD student in Power System and Power Electronics specialization of Electrical Engineering Department at IIT Bombay. Let us start with today's session. We'll be following the same procedure or agenda which we have been following in the past three sessions also. We will discuss the overview of week 4 and then we will take some questions. These are the deadlines for assignment 4 and 5, February 19th and 26th. Please submit the assignment on time. And you can find the links for all the PPTs and even the video recordings of these sessions on the portal itself. I hope you are able to access those recordings as well as PPTs. Let us start with the overview of week 4. In last week, we discussed initially, in the first week, we discussed about the introduction to smart grid, architecture of smart grid, different standards. Then we discussed different technologies and elements which are there in smart grid, which make the grid smart, which contribute to making the present grid a smart grid. And then we discussed about distributed generation. And in that we discussed mainly two types of distributed generation. Do you remember what are those two? Which two distributed generation or distributed energy resource DERs we discussed in this course till now? You can type in the chat box also if you want. Anyone? And first was solar PV and then wind turbines. In the next week, we also discussed one more element of the smart grid, which is energy storage in general. Energy storage system, and a type of it is battery. And as the penetration of renewables increase, we discussed in the last week, battery can help increase the penetration, can help these resources provide around the clock power. Because battery can store the energy and can discharge it when these resources are not available. In this week 4, we'll be discussing about this wide area monitoring system. While we were discussing the elements and technologies for smart grid, we had come across this SCADA. It is technology for. Can you tell what is the full form of SCADA? Supervisory control and data acquisition. And for this, we also read about RTUs, which are the basic elements used in SCADA technology to receive information from different devices, hardware components. And again, if you want to give some, you want to take some control action, that is also possible because of these RTUs. There are, and it's an old technology, SCADA. But after that, it's SCADA. The successor of SCADA is WAMS, Wide Area Monitoring System, and it uses a different block or element. Instead of RTU, it uses PMU, phasor measurement unit. Here, the SCADA provides us magnitude of current, magnitude of voltages or power flow or current. No angle information is available. Second, the samples which are transferred or transmitted, which are transmitted control center. It happens one sample to sample transfer rate is one sample every 2 to 4 seconds. It's a very slow refresh rate. Okay. And then there is no time synchronization. If we get a sample between every 2 to 4 seconds, then the processes which happen, the dynamics, power system dynamics, which have very high frequency and which such processes, transient phenomena which are completed within 1 second, that cannot be studied. Those phenomena we cannot study by these uh, by SCADA information because these samples are received every 2 to 4 seconds. What is happening between let's say first sample is received at t is equals to 2 seconds and second is received at 4 seconds. I don't know what is happening in between. How the system reached T2 from T1. What was the dynamics involved in that? Was the transition stable or unstable? Or what led, if it was unstable, then what led to that instability? That cannot be known from only this information. It's difficult. So these are disadvantages of SCADA. And that's why we wanted to move to PMU based monitoring system. Earlier, the blackouts which had happened, every time when a blackout happens, when the post-mortem analysis of that blackout is done, committees are set up to find out what went wrong. The one important finding or suggestion of the committee is always that there is a lack of good grid monitoring technology. This, the Manhattan blackout, which happened in US, they pointed out the same thing. And after that, this PMU came into picture. SCADA, and then PMU came into picture. So after Manhattan blackout, SCADA came. Before that, everything was mechanical, wired. Lot of wires were there, and also the visualization was not that good. Then SCADA came, and slowly, now we are into PMUs. And still in India, we don't have PMUs at all the substations. It is only there at 400 and above, 400 kV and above substations. The second phase will be now for substations at lower voltages. Okay, that's why it's very important if we get information at a faster rate, and we can know what is happening in the system close to real time. And also after we'll see what are other advantages in the next slide. We can also, let's say, certain 2012 blackout happened. In Mumbai, 2020 blackout was there. If we have PMU information, because its granularity is less, it has a sampling rate is very high. So we can get information at a smaller time step. And because of that, after an event, if we have a record of these profiles, voltage, current, power flow profiles, then we can actually know what things happened sequentially. What was the sequence that triggered that particular event? Using that data which is time stamped. SCADA data is not time stamped. We don't know the data which we are getting is for which time block. But here in PMU, it is time stamped. Each and every data is time stamped by using the universal time clock of this global positioning system. And that is why we know that for that each sample which we are receiving is for a particular time block, and that's why we can know what happened sequentially. And that's why we can know how the blackout progressed, how it started, and how it reached its final, how it took its final shape. Okay. Wide area monitoring system can help us in doing all these things. And there are many other applications which we'll see. And next thing which we discussed was phasor estimation. When we get data from PMUs are digital processors. They are signal processing devices. They use signal processing technologies, and that too, it all are based upon digital signal processing. The analog data, the input of these PMUs are the voltages and currents from CT and PT, current transformer and potential transformer. And these are analog signals, physical signals. But for phasor estimation, the PMU within its within PMU, these signals, analog signals, are first converted into digital. digital signals by sampling. Sampling is done, and once we have sampled signal, let's say this was the waveform, this was the actual current value, and we decided to, let's say, this is one cycle of 20 milliseconds if it is 50 hertz signal, and then we decided to have let me change the color, 8 samples per cycle. So this is one sample, this is second, this is third, this is fourth, fifth, sixth, seventh, and eighth. Okay. So these are 8 samples for each cycle. Once we sample the analog signal, we have only, if it is continuous, then we will be having continuous value for each time millisecond, depending upon the resolution of that meter. With the measuring device, we can get continuous values from 0 to 20 milliseconds. But here, once we sample the signal by using sampling techniques, we are getting only 8 values, 8 discrete values per cycle. And from these 8 values, we want to find out what is the magnitude of this voltage phasor. What is the RMS value and angle associated with it. So here we use discrete Fourier transform technique, which is one of the techniques. There are other techniques also. But this DFT is one of the techniques. We can recreate the signal from samples. And last thing which we discussed was digital relays. Okay, we'll see them one by one. These are the benefit in WAMS. We saw benefits of using PMU, SCADA versus PMU, which we have already discussed. Then the synchronized phasor measurement systems. It is called synchronized because each and every measurement throughout the system, it will be having a timestamp. We know for for what is the time right now? It's 6:20 p.m. Let's say 100 or let's say 10 milliseconds. And for this time instant throughout the network, wherever PMUs are placed, we know what are the value at those buses. What is the voltage phasor, current phasor at that particular time block, time instant. So it is synchronized. For each time block, we know everything throughout the system. And this is happening because of the GPS signal, the global positioning system, the navigation system, or positioning system, the navigation is one application of it. We are using that, and the GPS uses universal time clock. So everything is synchronized based upon this UTC. These are, so we want to, why from WAMS, what is our expectation? It is to ensure real-time monitoring, because now we are saying we are getting samples, 40 to 60 samples per cycle. That means 20 milliseconds is one cycle divided by 40. 0.5 milliseconds. One sample every 0.5 millisecond we are getting. So we can study all the processes in details at a very high granularity. Then, yes, we discuss this also. Post-disturbance analysis can be done because we can know the sequence of actions, which sequence of events that triggered a particular major event, because we know uh, values of these state, the system states. System state is given by voltage, current, voltage, power flows. Okay. Or in simple, if we know the voltage magnitude and phase angle and injections, then we can know many things, everything. So whatever minimum requirement, mostly V and theta, we find out voltage magnitude and the angle. If we know this, then we can know what is happening in the system. And adaptive protection, PMU, because it is giving us information at a very high rate, sampling rate is quite high, we can know the situation, how it is changing, and based upon that, the protection can also respond. For that, the protection has to be smart. It has to be adaptive. That we will see in the future weeks how the protection system can be made adaptive. And then last is power system restoration. When the system fails, when there is a blackout, how we can again restart the system. Teacher. Yes, yes. Then components of WAMS. So these are different components. First, we were discussing PMU. Then second is Phasor data concentrator from different PMUs. For multiple PMUs, there can be one data concentrator, and which then sends the data collectively to the control center. And then global positioning system. This provides that reference timing, the UTC signal, and then communication signal channel is the must for this. We want to send the data. The data is sent to the from PMU to PDC to the control center using this communication channel only. And once we receive the data or the control center has received the data, the next thing is to analyze the data. And by analyzing the data is several things can be done, and we'll see what are these different applications. So many applications are there based upon simply by using that PMU data. Many things can be done. And also we can visualize it, how the system is progressing by simple visualization over the screen in the control center. And because of the PMU, SCADA, with the SCADA also we are doing that, but now we are able to do it close to real time, and many phenomena which we were not able to study by SCADA, we are able to now study and monitor and take any actions for those events by using PMU data. And we will see two examples in upcoming slides. There are examples how the data from SCADA and PMU can give two different answers for the system state, two different estimation of the system state, and which are very different. That's why the granularity matters. And then by having all these capabilities, we are able to assess the system wide awareness of the system. This is a part. Its its sub block is the state estimation. So this uses the state estimation to know what is happening throughout the system. And one thing which we discussed last time also with SCADA, the state estimation is non-linear. But with PMUs, the state estimation becomes linear. And linear is very fast. Solving a linear system of equations is quite fast as compared to non-linear. Here we need to find out Jacobian and all that. And for a very large system, is challenging. And that's why many sparse matrix computation techniques are used in power system. Why sparse? Because Y max we see, that Y bus, let's say there are these three buses and the connection is like this: 1, 2, and 3. What will be the size of Y bus matrix? Can you tell? So in this case, let's say this is 4, 5, 6, 8. Okay. Can you tell what is the, and this might be connected to other branches also. Anyone? What will be the size of Y bus in this case? There are 9 buses. It will be 9 cross 9. The total 81 entries. First, we will be having all the diagonal entries, non-zero diagonal entries. And then we will be having entries corresponding to between these two buses. Say 1, 2, 9 diagonal entries and 2 entries each for this connection. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 2 each for these 9. So total 18 plus 9, 27. Out of 81, only 27 entries are non-zero. Others are 0. This is, I've taken a very small example. So more than 50% entries are 0 here. In power system, in a practical grid, let's say Indian grid where thousands of buses are there, one bus is not connected to more than 4 or 5 buses. There the sparsity means number of 0 entries divided by total entries. This is close to more than 90% most of the time. And sometimes it is even close to 99%. So 99% of entries are 0. Then what is the use of, there is no uh, use of storing these 0 values, because if we store them, we need to carry out operations every time by considering those values. Therefore, these fast matrix computation techniques have been developed so that without storing those 0 elements also we can do any kind of analysis, inversion, matrix inversion. For a 10,000 cross 10,000 matrix, inversion is a very costly affair. Very computationally heavy operation. Direct inversion is not done. LU factorization, QR decomposition, all these in state estimation with PMUs. QR decomposition is the most widely used technique for solving these linear system equations. It exploits sparsity. You can so all these techniques were developed so that the computation can be improved, and within very less time we can solve such a big system of equations where there are thousands of 10,000, 1 million equations. We want to solve them within seconds, in less than seconds. How to do that? Okay. So with PMUs, we are able to develop a linear system, linear state estimator. And but right now we are in the middle. We earlier we were having only SCADA inputs, and the future is to have all the inputs from PMU. But right now we are in mid, where we have both SCADA input also and PMU's inputs also. This is a linear state estimator. This is a non-linear state estimator. But now we are in between. We have to use both the inputs and do the state estimation. It cannot be linear. It can no longer be linear. Now it becomes a hybrid state estimator. How to solve it is an open research problem. Different people have suggested different methods. Which one is better? That that also we can compare. Okay. Then once we have awareness, we can do protection and control also. Then the process involved in WAMS. First is data acquisition, similar to SCADA, then transmission and processing. Application, we will see application, and then we will see synchrophasors and PMU. So these are the different applications for wide area monitoring system. It finds application at all the three levels of the power system: generation, transmission, as well as distribution. And okay, first we'll see generation, generator operation status. We can know by from the PME data, we can know what's the operation status of generator. We can monitor the transient angle stability. This transient stability phenomena are high frequency phenomena. The transients they involve high frequency signals. Sorry, because differential equations are involved. If we see the swing equation, if you take swing equation, then it's a differential equation, right? Swing equation is a differential equation. If you write down the models of generator model, because generator, when we show generator, we show like this three-phase generator. Right? So our L components are there. And when we want to study simple RL circuit also, then because of these elements, V voltage here will be D is equal to L di by dt. And here IR voltage drop. Differential equations will come into picture. And because of that, and let's say di by dt. And if you want to convert it into phasor domain, we can do that. Laplace domain d by dt, replace it by j omega. And the same is written as S. Because of these energy storing elements L and C, and there is interaction between these electromagnetic devices, electromagnetic elements. One is storing magnetic energy, one is storing electrostatic energy, and they do couple with each other. And we have these differential equations, and then depending upon the frequencies, and there will be different modes, different phenomena occur at different frequencies. And let's say in a particular event, any transient event, say there a signal, something, it's not like this. Let's say this was a transient behavior. And this is very simple, but there will be some noise here also. There might be some noise also. Now, if you want to see what are the different frequency components in this signal, there might be many, these small, these fast changing, these noise which we are saying, these are very fast, high frequency signal. And if you want to see, properly see the re accurately, we want to know how the noise is evolving or how this high frequency phenomena is evolving, then we need to simulate, we need to have the information at that particular time step. Let's say the frequency of this high frequency phenomena is 10 kilohertz. Then we need to know what is happening at every zero point 0.1 millisecond. This should be the data available with us. This should be the granularity of the data available with us. Then only we'll be able to study this frequency event. And for transient analysis, we require such inputs, and that PME is able to provide. With SCADA, it is not possible. We have already seen. That's why transient analysis can be done by using PME data. It will also not capture all the frequency events. It will only capture only up to what is the sampling rate of the PMU. Beyond that, it will not be able to capture. But that is also more than what we get from SCADA, much more. So this is for generation side. Then transmission side, we can do state estimation, power flow, optimal power flow in real time. Very quickly, we can know the state of the system because we are getting input at a very fast rate. Then economic dispatch, all these things can be done. In distribution right now, we don't have that kind of penetration. Neither SCADA nor PMUs. PMUs for distribution system are very costly. DPMUs, they are called DPMUs and they are very costly. But now some private these distribution companies like Adani in Mumbai, they have set up they have their own distribution network, and for that they have built a advanced distribution management system. It can do many things. It's really very advanced. It can even know what is happening with each of the transmission or each of the transformers. What is the oil level in the transformer? What is even the temperature of that oil? What are the gases present in that oil? Because of the presence of gas, the combination of gases which are there in the oil, it tells us what is the status of that oil. Means what status means what is the actual health of that oil. How are there any hotspots in that oil? Because even we can know the status of the dielectric strength of that oil. At different temperatures, different types of gases are released. And it's an indicator of the dielectric breakdown of the oil, which is there in the transformers. So with these advanced technology, we can do many things, and but it's costly. That's why it will take time. But yes, if we have that data, we can do many things. And another challenge with such a large amount of data is how to handle that large amount of data. Once we have in transmission system, there are 10,000, let's say 10,000 buses, but in distribution system, even in one city, there are lakhs of consumers, lakhs of connections. Each connection, if we have one smart meter which is giving data at a very small time step, then such a huge amount of data, how are we going to use it? And then requirement for data servers, data centers, data mining, all these things is also tremendous. And that increases tremendous. There are many challenges with that also. But yes, if we can use the data in substation automation, this line drop compensation for distribution system, one of the main problem, main issue, main challenge is to ensure that there is sufficient voltage at the far end of the feed. The voltage should not go below the permissible level of plus minus 10% or so. And automatic reclosing, if there is a fault in the distribution system, still right now it is manual. If there is a fault, the fault the resolution FRT team, it goes with the vehicle and searches out where is the fault, where is the fault. It's a manual process. It takes time. Sometimes it even takes 4 or 5 hours. Especially in cities, it's fast, it's quicker. But if you go out of city, then you will see the rural feeders, they face the problem. It will take around 4 or 5 hours to isolate that fault because rural feeders, their length is quite large. In the urban feeders, the length is small for feeders because number of consumers are more. The density is quite high as compared to the rural areas. Because the feeder is long, it takes time to locate the fault. As in transmission system, we have these distance relays and all that. We are able to get a idea of the length of the fault or distance from the particular bus where the fault has happened. But in distribution system, we don't have relays. We don't know that. All these things can be improved by using the WAMS in distribution system also. Once the isolation, the identification is done, localization is done. Once we know the fault is there, we have located the fault, then if the system is very advanced, it can even automatically isolate the system and connect the fault and means again restore the supply to the uh, this healthy section of the feeder. And then once the fault is cleared, it again connects the prior faulty section to the again to the grid. All these things are possible. The service restoration, backup by using means it can the we will see in the future weeks that let's say this is a distribution system and it is connected to the main grid at transmission level. And now in between there are many connections, interconnections. Generally it is radial distribution system, although designed in a mesh fashion, but operates in a radial fashion. There is a interconnection to ensure redundancy, but it generally operates in a radial fashion. Okay, operation is radial. Okay, let's say there is a fault here. And now this section becomes isolated. Look at this left part. And fortunately, but if we have, although it is isolated, but if we have here battery energy storage system, or we have PV, let's say it's a daytime, and some diesel generators are there. If not, then electric vehicles are there, fuel cells are there. And each house has these facilities, then they can sustain this. It will become a small microgrid, and these houses will be able to sustain their loads with the existing DERs they have on their rooftop or in their premise. Once the fault is clear, this coordination has to be done that the again it will be communicating with the grid. All these things can be automatically done. That will come under the automation part. Then feeder automation, automatic feeder switching. Here it was happening in if from ring to, let's say fault is there, ring to it becomes a, it's the ring, but if fault is there, then one section is isolated. So there is a change in the flow of current. So this is the supply, and the loads are connected like this in radial fashion. In a it's a ring, and there can be supply from. Now, if there is a fault here, if there is a fault here in this region, then this can be isolated. This one, but it can still receive the supplies. Is still there. Supply is still there. But now the current will redistribute. Automatic feeder switching can be done. One thing which happens in rural areas is that because in rural areas still electric 24/7 electricity supply is not available. What they do is in rural areas, one of the major uh, demand, the consumption is because of the agricultural pumps, and they are big motors, and they require three-phase power supply. So what they will give, even these agricultural pumps and these floor mills, you will find in rural areas. Then agricultural pumps, these are mostly agricultural pumps. In one village, you will find maximum two or three floor mills sometimes. So these two are the induction machines, and they uh, require three-phase power supply. So in most of the states, at least in Maharashtra, I have seen Rajasthan also it is there. They do a roster. So in substation, they have divided. There are different rural feeders. And let's say there are three rural feeders. What they have done, we have 24 hours are there. The first 1 to 8, 1 to 7. First 8 hours, the feeder 1 will be provided three-phase power. Next 8 hours, feeder 2, and last 8 hours, feeder 3. Those who are getting electricity in last 8 hours, they need to use agricultural pump at night. So they will plow their field, not plow, they will water their field at night. So this is switching of the feeder. This is manually done, but it can be automated. Okay, then feeder voltage control, feeder PQ control, and consumer side also. This we have already seen. Automatic metering infrastructure and automatic metering, meter reading. Here, this slide shows the synchro phasor, the PM, how PMU works. So these are the two buses, bus 1 and bus 2. If there is no reference signal, then we cannot compare the two signals. And say here it is shown, right? And this is the signal at bus 1 and this is the signal at bus 2. Okay, and if reference signal is not there, how can we compare? Without reference, it is not possible. In power flow also, we assume that the slack bus, the role of slack bus, one of the roles of slack bus is to provide a reference, right, for voltage angle. With respect to that bus, we know what is the voltage at other buses. Similarly, here, both the buses, this volt, let us say this is the voltage signal at both the buses at time t is equals to 0. And this is the reference signal generated from the GPS signal, the universal time clock. Okay, now with respect to this reference signal, we know that this voltage at bus 1 is lagging the reference signal by delta 1. This should be delta 2. And this voltage at bus 2 is lagging by amount delta 2 from the reference signal. Now we can know, we can compare these two values because the reference is same for them. But if there is no reference, then how do we compare? We don't even know if even time synchronization is not there. This reference is because of the UTC. You know, at this time the reference is this, which is 0. But if there is no reference, we don't know what these two values are coming from, which two time blocks. We don't even know which time instant. Therefore, the common reference signal at remote location is possible due to GPS time synchronization. And now we know this voltage phasor 1 is at delta 1, V2 is at delta 2, and they differ by delta 2 minus delta 1. So this is possible by PMUs. And then, yes, we discussed that in PMU they receive analog inputs from the analog voltage and current inputs from the CT and PT, the current transformer and potential transformers. So these are the analog inputs. Then this is the PMU, which will convert everything into the digital domain by doing sampling, and it receives one more input, which is the GPS clock, the UTC signal. And then the data is communicated to the substation or which can have a data concentrator, and then finally to the control center. This, if you see, it is showing how the SCADA versus PMU. SCADA only focuses on the local phenomena. It's a local control and monitoring aspect can be studied by using the SCADA data. But PMU can help us know both the local as well as the interconnection wide phenomena. Okay. This was the thing which I was checking, that if we have SCADA and PMU and we get data from both of them, both SCADA and PMU, because we know that SCADA output is received at every 2 to 4 seconds. It will not change much between 2 seconds. It will remain same. But if we see the PMU data in that same duration, there's a lot of difference. See the SCADA. If as per the SCADA data, it shows that this transient phenomena is stable. it is reducing, this value is reducing here. But as per PMU data, the system is evolving toward instability. It is going towards instability. It is increasing. The deviation is increasing. This oscillations are becoming unstable. Both the data are giving different picture. That's why it's important to know, to have the information at a much smaller scale, and which PMU is able to provide. The same thing here, you can see operating near the critical point increases the likelihood of voltage collapse. And if we, as from SCADA data, we will get to know this point every 2 seconds. We don't even know in between if we cross this critical point, then. But PM is because every 2 milliseconds, every 0.5 millisecond, we are getting the system state. We are able to know, yes, we are moving ahead, moving towards a critical point. Let should do something to make the system to avoid voltage instabilities. So these synchrophasor enabled apps, they provide insight into distance between the operating point and the critical point. That's why after PMU, so many analytics were developed. Here in IT Bombay, our answer labs, this project was done for PGCIL, Power Grid Corporation. Several analytics were developed here. So that's why there are many application of these PMUs. It makes our life more easy. So this was the first part, and the next part was the phasor estimation, which is once the PMU receives the data, it has to estimate the voltage and current phasors. SCADA measures the voltage magnitude, current magnitude, and power flow between the lines connected to that particular bus. We know the voltage and the power flow on the lines connected to that bus, voltage magnitude only. But for with PMUs, we get voltage phasor as well as current phasors. And how do we estimate these phasors based upon the analog input that we receive? And that is what we study here in phasor estimation techniques. So first of all, it will be converted to digital signal by appropriate sampling, and then there will be analog to digital converters, and then this phasor estimation techniques will be used. Phasor estimation and frequency estimation. In phasor estimation, there are many techniques: full cycle, half cycle, cosine. Similar to cosine, sine transform can also be used. Recursive DFT. It's a we'll see why recursive is used, and then least squares estimation is there. Kalman filter is there. Mimic filter is there. There are many techniques. And the most widely used technique is the recursive DFT technique. Okay, we'll see questions and we will do problems on this DFT also. In between, there are problems on DFT and least square. That will take time. So let us start with questions. The first question is, which of the following is not a non-operational data in WAMS? So in WAMS, there are two types of data that are transmitted. One is operational and one is non-operational. So can you I recognize which of these is not non-operational data. Anyone? Voltage and current phasors. We have. Hmm. Yes, we have to see this. It is not a non-operational data. It's a operational data. Operational data is a continuous stream of data which we receive continuously. The measurement of this voltage and current phasors and the breaker status. This breaker, these are continuous values, and this breaker status will be binary, 0 or 1. So this we get from PMUs. And then periodically pulled at specific time interval. These non-operational data are they are sent or transmitted at some specified time intervals at some period. An example of such data are records of multiple events like series of fault, power fluctuation, disturbances, and lightning strikes. Lightning strike will not be happening on a regular basis. It will happen uh, once in a while, and these events are tracked, and then after the event, they are sent. That information is sent. So these are like fault. Fault is not a normal phenomena. It was not a regular phenomena. Whenever on a regular basis, some these information are sent to the control center by these digital fault recorder, relay, and circuit breaker monitor. And next is which of the following estimation techniques can filter the exponential DC component inherently? Yes, which what's the correct answer here? D. All of the above. D is not the correct answer. Is in both discrete this DFT and cosine transform. Actually, cosine transform has been derived from both these are type of DFT only. Means this cosine transform is used to reduce computation, but both are type of DFT. And in DFT, we find out by using DFT, we find out only the magnitude of the phasor and the angle. RMS value of voltage and current phasor and the angle. These two things we can find out. In least square estimation, if the signal has a DC component also, that also we can find out. We will see how it does. And then cosine and discrete are almost they're same. Mm, it uses the fact that cosine can be transformed into sine by just shifting the signal by 90 degrees. we know that this is sine. This is a sine wave. And if we simply shift it by 90 degrees, then it will become cosine, right? If the if this is 10 sine omega t, and then this is, and this is 10 cos omega t. All the values will repeat. If if I simply shift signal, this signal, this red one to by 90 degree, minus 90 degrees, then it will become same cos, right? Same values. I can use the same values. So this principle is used in cosine and sine transform. So we need not calculate all the values again because we know that after 90 degrees that same value will be repeated. So there is a lag of 90 degrees between sine and cosine. So we have real and imaginary part. Let's say A is a phasor. Then let's A, not A, let's say V is the voltage phasor, and this can be written as V real plus J or I V imaginary. Okay. This is also V cos theta plus I sin theta. Right? Now because I know the values, I know that by shifting the sign by 90 degrees, I can convert it into the cos. So if let's say this is t at instant t, then theta t. If I'm calculating cos theta, then sin theta I can calculate by using cos of theta minus pi by 2. Okay. I need not find out this again. I can use this theta value of, let's say, uh, in one cycle means 2 pi. There are 8 samples. Then for 90 degree, how many samples will be there for pi by 2? Anyone? In 2 pi, in one cycle, there are 8 samples. How many samples will be there in 90 degrees, pi by 2? Yes, correct. 2. Only 2. We can use the same theta t minus 2 if 8 samples are there. Uh, uh, the value which was there for t minus 2, we can use the same value. It will no need to compute sine of theta. So this is used in cosine transform. Similarly, we can do it for sine also because sine can be converted, cos can be converted into sine, and vice versa. Then this is the next question. Number of zero crossing of a signal is 5. There are 5 zero crossings in the signal. Its first and fifth crossing occur at 20 millisecond and 0 millisecond respectively. The estimated frequency of the signal by zero crossing detection technique is, you need to calculate this. In slide there was one formula mentioned for this. So do you remember? To try this, How will you solve this question? And so these are the 5 crossings. And fifth crossing occurs at 20 millisecond, and first and fifth occurs at 0 and 20 milliseconds. So one is at 0, one is at 20 milliseconds. Now, how do we find out frequency for the signal by zero detection technique? Anyone? Let us consider this. Signal, sorry, 100, correct. I think 100 is correct. How did you find out?
Actually, from the drawing, you can see 2 cycles is 20 milliseconds.
One cycle will be 10
One
milliseconds.
cycle will be 10 milliseconds, and frequency will be 1 by t, 1 by 10.
Yes, correct. Good. So we can do, even if we take this one cycle, in one cycle there are 3 crossings. So it is like this m minus 1 by 2 into 1 by t2 minus t1 or t1, whatever. Same thing what we have said. Here m is 5, so 5 minus 1 is 4, by 2 is 2, multiplied by 20 minus 0, that means 20, and it is milliseconds. It becomes 100 hertz. Okay, is this fine?
Sir, I think it should be 0 millisecond to 20 millisecond respectively in the question. It
Yes,
has
yes.
written that it's the first and the fifth crossing occurs at 20 millisecond and 0 millisecond. It should be, I think, 0 millisecond and 20 millisecond respectively.
Yes, correct. I will change that. Is the two values have been interchanged. Okay, so let me change it now only. So this should be 0 and this should be 20. Okay. Next question is this. Now it's a numerical problem. Here we'll see how to find out DFT. So the question is, we have been given 8 samples. Sample values are already available. Consider the sample given below with a fundamental frequency of 50 Hz. Fundamental frequency is also given. And first question is, calculate the sampling frequency and sampling time. Now, how will you? Second is to estimate the phasor using full cycle and half cycle. So how will you do the first question? The samples are given and fundamental frequency is given. How to find out the sampling frequency here?
Actually, from the given, we can see in 20 milliseconds time, 8 samples have been taken. That is 8 by 20 will be the sampling frequency.
How do we know that it's 20 millisecond?
The fundamental frequency is 50 Hz, means 1 by
Okay.
50.
Yes, 1 by 50. So what will be sampling frequency now?
Actually, we have they have given 8 samples, right? That's when in one fundamental cycle they have taken 8 samples, means 8 by 20 with the sampling frequency.
Yes, so sample time is 20 millisecond divided by 8. Sampling frequency is inverse of this. Correct. So how much? What's this value? Sampling frequency is equals to sampling time is 2.5 millisecond and sampling frequency is 400 hertz, right?
Yes, yes.
So this is his equation. The next part is to calculate the DF, to estimate the phasor using DFT, full cycle and half cycle. Procedure is same for both. In half cycle only 4 samples are to be considered. So 8 samples are for one complete cycle. In half cycle, we consider only one half cycle, first half cycle. Since there are 8 samples for 2 cycles, for one cycle there are 4 samples. And for half cycle, only these 4 samples are considered. For full cycle, all the 8 samples are considered. So here you can see this is a simple way of doing it. What you can do here. You can calculate this 2 pi n by n. And this is a formula for calculating this phasor estimation, and then this will be used for minus 2 pi n by n. If we expand this, it will become Vn cos of 2 pi n by n minus j psi n minus j Vn sine 2 pi n by n. Now what you can do is 2 pi n by n. Calculate this 2 pi n by n for all the values of n. This will be, if it is 1 to n, here we are starting with 0. Then it will be n minus 1. Okay. If n is 0, this is 0. If 1, pi by 4, pi by 2, 3, pi by 4, pi up to 7, pi by 4. If you start it from 1, then it will be pi by 4 up to 2 pi. but answer will not change. Then calculate cos 2 pi n by n and calculate sin 2 pi n by n. Now it is simple, right? Just take cos of this value and next time take sine. Cos 0 is 1, sine 0 is 0. Pi by 4 is same. Pi by 2, this becomes 0, this becomes 1. 3 pi by 4 means second quadrant. Sine is positive, cos is negative. And then it becomes pi. So we are moving like this. 0, then this. So at pi it becomes, cos becomes -1, sine becomes again 0. And then third quadrant, finally reaching to fourth quadrant. So this is this value, 3 pi by 2. Then we have to multiply this x in these sample values into cos and sine. Because this is negative, this negative also is there. Then calculate all these values. Then sum these values. So this is the real part and this is the imaginary part. If you want the magnitude, then square and add and take root and divide by 2 by n. So this is 2 by n here. This is for full cycle. If we want to do it for half cycle, then n is replaced by n by 2. In that case, in this formula, replace n by 2 and then solve the same way. Everything will be same, just out of it, we'll be having only 4 samples here. The final value is 2 by n multiplied by root of the absolute value of this. This is complex number. X is a complex number here. If we take the absolute value, then we will get this and multiply it by 2 by n. And for angle, take tan inverse of imaginary by real. Okay, is this fine? This is simple, right? Similarly, for half DFT, we can do. We need only 4 values here. N by 2 is 4. And in both the case, you can see here the magnitude is 220.47. Here the magnitude is 225.52. Not much difference, but here because we have lesser number of samples, this deviation is more. If we increase the number of samples, the deviation will be very less. If we take 1 kilohertz frequency, that means how many samples are there? For 1 kilohertz frequency, can you tell what will be the number of samples?
20.
Yes, correct. Because you can, number of samples is equals to sampling frequency divided by the fundamental frequency. If sampling frequency is 1 kilohertz, then what is the fundamental frequency? You know, time period is, no, fundamental frequency is 50 hertz, right? It is 20 samples. If we take 20 samples, this difference will further reduce. And if we take 40, then it will be very, very less. They will be close enough. And angle difference here it is 70.03 minus 70.03, it is 69.9, very close. So as we improve, increase the number of samples, half cycle will also give, result in result in similar values. So when we do cosine or sine transform, we don't calculate this. We don't need this. We don't need this column also. In cosine transform, we will do what we will do. We will take it's here number of samples are 8, right? So for 90°, the difference pi by 2 corresponds to 2 samples. So for third sample, P is this third sample, this value will be this we need to calculate. This will change. We can use the previous t minus 2, the value which is there at t minus 2. Yes, t minus 2. That we can use. Because here you see this is 3, right? This value is repeating here. After this is this was at t is equals to 1. And this is at t is equals to 3. Or for third sample. This is for n is equals to 1, sample 1, and this is for n is equals to 3, sample 3. So there is a difference of 2 samples. After that, all the values are same. These values are same. So no need to use this. For third sample, directly use the value of cos t minus or n minus 2 and multiply by this. Okay, correct. So here xn is, you can see xn is this, right? 210.7331. Now, what is the value of cos? Let's say this is n minus 2. N is 3 here. So what is cos of 1? Right. Cos of 2 pi by n. And this is n minus 2. Something right here. Cos of 2 pi by capital N is common. And this is n minus 2. Now we are talking about n is equals to 3. So what will be this? N is equals to 3 is cos of 2 pi by n, correct? And cos of 2 pi by n is this 1. And to multiply this by xn, you will get same minus 210.7331. So we are not, this column is not there. We are not calculating sine. We are using the cos value itself. But previous cos value 2 samples before. The value which was there 2 samples before the current sample. We are using the same value. In this way, we can do cos transform. Similarly, we can also do sine transform. In that case, we have to use the sine value before 2 time logs. This one. The arrow has changed now. I will say this one. Sorry. So we have calculated sine, but for cos we have to take 2 time blocks before values which is there 2 time blocks before. Yes, one. But only thing here will be you have to take care of this minus sign here because we are taking we are calculating this term which is already with a negative sign. And if you want to calculate this term, then you need to multiply it by -1. That is why this value is negative and this is positive. So this we have to take care. Okay. So you can use full cycle, half cycle DFT, cosine transform, sine transform. All these are different types of discrete Fourier transform techniques. Is this clear? Do you have any doubt in this DFT? Calculating, estimating phasor using DFT. This is what this is what we have done for 8 samples. Let's say um, this is the voltage signal. Mm, and we are considering we are calculating the we are performing DFT over these 8 samples. Right? This is a window of 8 samples. First 8 samples. Now let's say this is 1, 2, 3, 4, 7, 8. Okay. And this is the ninth sample. And then so on. Now there are two ways if you want to continuously find out the DFT of the input signal. We have only now found the DFT for one cycle, but I want to do it continuously. Now I want to do it for this. And not just this, I want to find out this actually. For continuous basis, I want to find out this one. I will remove one sample from this. Let's say this was these were the 8 samples. We have more samples, 9 up to 16 also. First DFT is, let's say this is first DFT V1. Now this is the value for second. But now I'm not doing like this. What I'm doing is 8 samples. I'm taking only 8 samples, but now I am calculating DFT like this. Remove the first sample and add one more sample. This will be V2. V3 will be remove this sample and add one more sample. This will be V3. Now, for doing this, we have two ways. So I am removing one sample, adding one sample. Removing one sample and adding one sample. This can be done in two ways. One is for each of these windows, this is called a window, and each window is having 8 samples. For each of these window, I perform this again, this DFT calculation again. each time perform, or for each, let's say, for each window perform DFT. Second option is for this, I know the value of phasor from this first window. Now, can I do add something or just do something? Use this value. V2 is some function of V1. Use this value and directly find out the V2 without doing the DFT again. This is the second way. Use the phasor value from previous window. So this is called iterative DFT. We are iterating every time calculating, doing DFT. And this is called a recursive DFT. We are doing DFT only once. And then for remaining windows, we are simply using the previous value, the DFT calculated in the previous window, and simply updating it. It is a recursion. It's a, we start with 0, add 1, 2, 3. So we added 0 and 1. Now add 1 more into it. Sum is 2, add 1. Is this clear? Difference between iterative and recursive DFT?
Excuse me.
Yes.
So why do we need to do DFT for each window? Why can't we do continuous, suppose two cycles is having 16 samples, means you can't do DFT of 16 samples at a time?
But that will give us only one value, right? But when we are seeing, let's say, let me show that figure. Let's say we are talking about such kind of a profile. How will you get this profile if we for this entire time block, let's say I have 500 samples for this duration and I perform one DFT, then I will get only one value of voltage, right?
Okay.
I will not get a profile.
Okay.
Profile is only possible when I continuously do it. Let's
o-
say I do it for first 8 sample, then I add, then let's say at this time block, there is a fault and there is a sudden drop in the voltage. Then I will see that if I do like this, remove one, add one sample, then I will see a drop in the voltage suddenly.
Okay. Good.
So to continuously determine the phasor value, we are doing this.
Okay. Okay.
But every time calculating DFT will be a computationally intensive process, right? Again, we have to take cos, we have to take sine, then multiply and then add. So many operations are involved in one DFT calculation. So if we use recursive, then do it only once and then simply use addition or subtraction.
Okay.
You have a function in terms of previous value and then just use that function.
Okay. Means we are adding one sample and we are minusing the one sample, right?
Yes,
In
yes, we
recursive.
are
Means
in
we are
both
getting.
in both iterative and DF recursive we are doing the same thing. We have a window of number of samples depending upon the sampling frequency, and we are moving that window. It is called moving window. We are
Okay.
simply moving. How are we moving that window? By removing one sample and adding one sample. Removing one sample from the previous window and adding one sample from the next window.
Okay. Got it.
We are simply moving the window, keeping the number of samples same for the DFT calculation.
Means for each sample, we are finding voltage and phase angle at each sample, right? By
Not for
using
each sample, but for each window.
okay. But
But
when you are drawing the profiling, you are taking for each fundamental cycle or each sample. This one, what are the profile you are drawing?
that
No?
that is for a cycle only because DFT calculation requires samples, and that's why we create windows. Whatever sampling frequency is there, depend that will decide the size of that window. And for that window size, we have to continuously do the DFT.
Okay, whatever the magnitude and angle we are calculating using DFT is for particular
Hmm.
fundamental cycle, right?
Yes, it is for the fundamental component only.
Okay, okay.
Okay. Any other doubt on this recursive and iterative DFT? So that's why the common practice is to use the. So which one would you like to use? Iterative or recursive? What do you
Mm,
think which one is better?
recursive.
Yes, recursive is better because we just have to
It's the time of the
calculate DFT once. It will save the time. Computation requirement will be reduced. Okay. The next question is advantages of the digital relay are self-checking, functional flexibility, system integration, auto reclosing, all of the above. Which option is correct? All of the above, yes. All the above is correct. Self-checking, it can detect what's the problem. Function flexibility, one relay can be configured as distance relay also over current directional. Same relay can be configured differently depending upon the requirement. Okay. Match the following for a digital relay. RAM, ROM, and EEPROM. You have to match. Which one will match? Correct matching. RAM is for which one is for storing program permanently?
Rome.
Yes, ROM. Read only. And RAM will be for
Supporting change of relay parameters.
hmm, RAM is like a scratch pad. Whatever computation we want to do, for those computation, the temporary variables, let's say we while doing this DFT calculation, we found these columns, right? We found these value costs of 2 pi n by n, sine 2 pi n by n. Then this did some square root. These are temporary values. Finally, we require only these two values. But in between, these are so many temporary values. These are stored in RAM. It is a scratch pad during algorithm execution, and EEPROM is it can be changed. That's why it is programmable, electronically programmable ROM. So we can change it. It supports change, but we don't want it to change frequently. Relay parameters are set for a duration. Uh, unless the system changes, we don't generally change it. That's why we want to keep it but it's a variable constant, I would say. Although it is constant, but it can change, but not frequently. For that purpose, EEPROM is used. So it is read only, but it can be changed if required. Okay, correct. Then next question is, in digital relay, the reliability is defined as. Which option is correct? C. Its answer is this. Number of correct trips divided by desired plus number of incorrect trips. This should be bracket here.
How A and C are different?
A and C. Number of desired trips plus number of incorrect trips. Is there a difference between A and C? If A is equals to C, that means total number of trips is equals to correct. Total number of trips is equals to desired number of desired trips plus number of incorrect trips, right? How it's different, you can see. Let's say there is a fault. Okay. And the relay should have tripped for the fault. This was the desired behavior from the relay. Tripping on the fault. Okay. But if it now there can be two possibilities. If it trips, okay, let's say if it relay trips. Now there can be two possibilities. First one, it trips correctly. Trips whatever it was meant for overcurrent tripping, it is tripping for that reason. Second is it's not, it is incorrect. This correct and incorrect will come when relay actually trips. If it trips for the correct reason, then it is the desired only. We wanted, that means that is the best option, best behavior. But if it trips, but it trips for incorrect reason, then it is not correct. And if relay was supposed to be tripped, but it didn't even trip, then that is undesirable. Did you get this point? This
Actually,
A and C
what?
are
Hmm,
A and C are
what?
not equivalent.
Yes, I got it. Means in if the actually if relay is desired to trip but it doesn't trip means it cannot come under total number of trips, but it can come
Yes,
as a part of the number of desired trips, right?
yes.
Yes, got it.
So A and C are different. Many times it happens that relay doesn't even trip. Or sometimes it happens that relay tripped for it was not supposed to trip, but it tripped. The incorrect will come when it is tripping, but it is tripping for a different reason, which it was not supposed to trip. So that is an incorrect trip. But if it doesn't even trip, then it is undesirable. Okay. So reliability of relay comes when it trips. So this is total number of trips. So trips can be tripping. Relay operation is to trip. So if it trips, there can be two options. First, it was tripped on desired event. Second, it was tripped on incorrect event. So these are the only two possibility when it trips. Third possibility is that it doesn't even trip. So that will come in dependability. How much dependable the relay is. Okay, so out of this total number of these trips, desired plus incorrect trips, how many are correct? Assignment, see, sorry, there is no assignment the same question for which correct answer is C. In this assignment,
Sir,
which question are
assignment,
you talking?
I think assignment third assignment.
No, third assignment, which question?
No, so this question is not there in third assignment, I think.
I'm looking, I'm telling you.
Okay. Okay, till that time, let's move to the next question. I have to stop sharing. Share again. Is it visible now? Okay, this is the next question. How many samples must be shifted in the cosine DFT in order to obtain sine? This
C is the
also
option.
n
C.
by 4. Yes, correct. Correct, because it corresponds to 90 degrees. Size of augmented matrix in the least square method depends on. Do you know answer for this? Anyone?
No, sir, I haven't gone through this topic till now.
Okay, no problem. Answer is sampling rate. We will see it at the end. The next question is, using a full cycle DFT phasor estimation, phasor is estimated for a voltage signal with a fundamental frequency of 50 Hz and a sampling frequency of 2000. So how many samples are there? Number of samples is equals to,
40.
is correct, 2000 divided by 50, 40. The estimated angle for V 80th V80, that means 80th window is 30 degrees. Now we want to find out the phasor, voltage phasor, the angle of voltage phasor for window 83rd window. So how will you calculate this? What is the procedure?
360 divided by 40 gives the each sample
Degree angle for each sample.
yes.
Okay, so that is 9 degrees. Then what's the next step? Oh, there is one. So what's the answer? Are the options correct? What should be the answer? Here. You were saying correct. And what will be the next step? 360 divided by 40. Then,
I'm a little confused about what is this V80 and V83, what it will be.
no, we were discussing right that we calculate DFT for a window. So
Okay,
these
this
are
is
window
88.
number.
Okay.
These are window number. 80th window and 83rd window.
Means the difference is 27 degrees, it will be there, right?
Yes, correct. But this there is a typing
50
error here.
answer will be there. 57 it should be.
Yes, so answers are not correct because this answer will be B 39 degrees if the angle is asked for V81, correct?
Yes, yes.
Yes, so for V83 it will be 57 degrees. No, 50. 57 degrees. Yes. For this V81, it will be 39.
Yes, right.
Still, again, it is not going forward. There is some problem with this laptop. Oh. Next question. Maybe let us stop here. I think it is creating problem. We will continue next time. And I will share this PPTs. You can go through the questions. Is it fine?
Okay.
Yeah, because there is some problem. I'm not able to share again. Okay. Okay. Thank you. If you have any doubt, you can ask. I will stop sharing. I have already stopped sharing.